So there were no questions in the 1 minute papers last time, which might be good, might be bad, I don't know. But that means that we can get straight into today's lecture, I suppose, which is about monads. So we have secretly been aiming for understanding what monads are in the last few weeks, right? So we introduced categories and functors and so on. And my motivation was that I wanted you to understand what's actually going on in Haskell. So let's have a very quick refresher what it looks like in Haskell. Let's have a load up GHCI. Then I can ask what is a monad. And we see that we have a bunch of instances, and we also told what the monad is according to Haskell. So it says that if M is applicative, then to make M into a monad, you have to implement these methods. So you need to have some kind of bind operation. You can have a bind operation where you don't actually use the second thing, and you need to have a return. And if you look at what an applicative is, before we forget, then we see that that's also something where you have a pure that's the same as the return. And then we have this app operation, but F needs to be a functor first, right? So if we have a functor, then we can make it into an applicative, and then we can make an applicative into a monad. And if Connor was here, then he would rant about how this is the wrong way around, because if you have a monad, then you can make it into an applicative in a canonical way. So this constraint here is not really needed. But that's the way it's been set up. Whereas, and in the same way, if you have an applicative, then you can make a functor. So really what you want to do is you want to implement the monad things, and then you get the other things for free. There will automatically be functors and applicatives. But let's focus on the monad one. So what do we need here? So we have a return, which says that we can make a pure thing into something in the monad. So this is how we think about it in Haskell, right? We think of the monad as some kind of effectful thing. And return says that, well, you can always embed non-effectful things into effectful things. And then we have the bind, which is what's used for the do notation. So this says that, well, if I have one first effectful, I can think of running it, and then I get a pure A, and I have a second thing which depends on this pure A, and then in the end I'll get an effectful B. So the do notation desugars to this, where you put in the thing here, and then you get an X that you bind on the left. That's this thing of type A, and then you have the rest of the computation. And that's how it works with the do notation in Agda as well. So that's kind of a good operational way to think of these things. So effectful operations can embed non-effectful things, and you can chain effectful things together like this. But it would also be nice to understand where it's coming from, right? So that's why we're going to look at the category theory definition. So with that in mind, let's switch back to here. And so this is how a monad is defined in category theory. So you have a functor, and then you have some extra structure on this functor, right? So again, it's different ways to phrase things. So here we like to phrase it as having a functor plus extra things, a little bit like we did in Haskell, right? And what's the extra things? Well, so first of all, we want to have a monad on a category C, not just on the category of types in Haskell, right? But for an arbitrary category C. And we can see that we still want to have the return, but for things to play nicely, we want these things not just to be single maps, but actual natural transformations. So remember in Haskell here, the type of return is A to M of A, right? So this A is universally quantified. You can put in any type A you want here, and you're going to get an M of A out, right? So you can do a return of 7, and then A is int. You can do to return of false, and then A is bool, and so on, right? So the way Haskell works, by just mentioning a type variable here, we're saying this should work for every A, right? And that's kind of like the way the natural transformations work, right? So we're saying that you have one component for every object in your category, and they have to play nicely with the F maps involved. So the natural transformation for return says that we have a natural transformation from the identity to M. So if I apply this at component A, then it goes from identity of A, which is just A, to M of A, right? So exactly like in Haskell, go from A to M of A. And then the way it's nice to phrase this in general for categories is not having a bind, but rather having the join, which you also have in Haskell, right? Well, if you load control.monad. So this says that if I have 2 layers of M, then I can join them together to get 1 layer of M. And as we will see, it's equivalent having a join and a return and having a bind and a return. But the nice thing is that this type here makes sense in any category, right? Because saying if I apply the functor twice, then I should have a morphism to applying the functor once. And that's exactly what this join transformation says. It's saying that it's a natural transformation from M composed with M, so that's M of A, to M, so M of A, right? So one good way to think of this, I think, is that having these 2 operations means that we can turn any number of layers of M into exactly 1 layer of M. So the return says that if you have 0 layers, you can blow it up into 1 layer, probably vacuously, not introducing any kind of effect or anything like this. And the join says that if you have 2 layers, you can turn it into 1 layer, right? So then if I use join a number of times, I can turn 3 layers, then into 2 layers, and then into 1 layer, and so on, right? And I can turn 17 layers into 16, 15, and so on. So having return and join says exactly that you can turn everything into 1 layer of M. And then we have these laws, as you would expect, and they tell you what happens when you turn things into this 1 layer, right? So I think it would make sense to look at them on the document camera. So let's see if we can make sense of them. So the first one says, well, if I start at M of X, then I can turn this into M of X by returning, right? So I'm taking this thing and I'm making a spurious outer layer. And then I can join this back down again, combining these layers. It's going to take me to M of X. And this first law says that that's not doing anything at all. That's the same as just doing the identity on M of X. So if I make a fake outer layer here and then join it back together, I get back to where I started. That's this return join law here. And we could also consider doing something similar. If I start with M of X and then I make a fake inner layer, so I'm turning this X into an M of X, and then I can use the functor instance of M on the outside. So do an F map of return. Okay, then I also get to M of X, but it's still a fake layer, so if I join this back together to M of X, that should again be the same as doing nothing, just staying, right? So these 2 laws says that, well, if you make something fake and then join it back again, then you didn't really do anything, right? You could consider doing the other thing, where if I start at M of X, then I join these 2 layers together to make an M of X, and then I inflate it. Gets me to M of X again, right? Then you could think, well, should this be the identity? So this is saying join 2 layers together and then make a fake layer. Yeah, so now we lost some information because we used to have 2 layers with their own effects, we joined them together, combined them somehow, and then we made a fake effect, right? So this should not hold in general, and it does not hold in general, right? So there are monads where this is not true, but this will always hold for all monads we care about. Right, and the final law, the join-join law, says that if I start at 3 m's, then there's 2 ways I can take that down into 1 m, right? I could start by joining together the 2 outermost things. So that's going to turn these 2 m's into 1 m, and then the m of x stays on the inside. And then I can join that again. Yes. Which takes me to m of x. Or, if I just write it again, m. I can start by joining together these 2 inner m's by f mapping a join. So that keeps this m on the outside because I'm f mapping, so I'm working inside. And then I'm joining these 2 together into 1 m. And then here again I could join, right? And the join-join law says that it doesn't matter if you first combine the outermost 2 m's and then the inner one, or if you start with the innermost 2 and then the outer one, right? You get the same result, which also makes sense again, right? If you think about it. What doesn't make sense is to say that already at this stage they should be the same, right? Because again, it would type check to ask for an identity here, right? But if you think about what this would mean, it doesn't really make sense because then you combine different layers. So it's too much to ask for that these things will be equal. Right? So we shouldn't expect that, but if we go ahead and join the missing ones, then we would think of it to be the same. Right? So it's a good exercise to try to think of specific monads where these 2 things are not the same. I think that's not very hard. And similarly where this law does not hold. Right? And also notice that all of these equations we have, we always end up in m of x, right? We never end up in x, because there's no way in general to get out of the monad, so to speak, right? If the monad is something like IO effects, so that's the main Haskell monad you care about, right? Saying that we can get an x and we have the side effect of making some input-output, writing to a printer or whatever, then there's no way you can really escape this side effect of printing, right? So in general, the return says that I can go into a monad, but there is no co-return that goes out of the monad. Right. Okay, so how does this relate to the Haskell definition? Well, let's see if we can define a bind, except that the bind we have here is not very category friendly in the sense that it involves this function type as an object somehow, right? So it's having in the middle we have a function from a function type. It's a higher order function, but we can rearrange this. So rather than taking this argument first, we could just rearrange it and say that, well, if I have a function from x to m of y, so that's this, let's rename it maybe. So this is a and b. So I have a function from a to m of b. Then I can extend that to a function from m of a to m of b. That's the same thing as this, right? Except that I swapped this argument and put it here. But then it makes more sense because then I can talk about 2 different HOMs. Right? Okay, so let's see if we can do this. This A and B again. So what do we have? So we're just assuming we have a monad, and we want to get a morphism from that functor, the monad applied to A, and then to that monad applied to B. Right? And we have this F, which goes from A to M of B. Okay. So how should we think about this? Well, the first thing is, the good news is that we are trying to get into the monad applied to something, right? Which means that we know that we can always get into exactly one layer of the monad as long as we can get into some layer of the monad, right? So if I could get into B, then I could just use the return. And if I can get into the monad applied to itself 17 times, then I can use the join to squash it back together, right? So I don't have to be afraid of getting too many applications of the monad in the right. So in that sense, I could try to apply the monad to F. So if I do F map F M, then so F went from A to something. So if I now do an F map of M, then I goes from M of A to something, which matches my source here, right? So that's good. So maybe we start like that. Okay, but now we have to get from M of B to M of B, but that's exactly what the join is doing for us, right? Right, so if we have a return and a join, and M is a functor, then we can derive the bind. And I'll leave it as an exercise to go the other way, to say that if you have the bind and the return, then you can really derive the join. So these are different ways to phrase the same thing, but this one is a little bit more friendlier to phrase directly in category theory. Okay, so let's see if we can look at, so does that make sense, first of all?
See that at the end you were asking the goal, and you had in a line, and you just press the key manually if something fit.
Right, okay, let's look at the last one again. I think it might be a little bit annoying. So, okay, so what is the goal? So it's a home, fair enough. And it goes from the action of functor applied to the action of functor applied to B to the action of functor to B. And the thing that maybe I was trying to get away with too quickly is that I defined M to be functor to make it look a bit nicer. And if I look at the type of join, okay, then it says that if you give it an object, that's the component you want it at, then now it exactly matches. So if I give it component B, okay, so maybe this is the thing, that if I don't fully normalize it, then the goal here is talking about M, because that's what I put in the type signature. Whereas the thing I have is talking about functor, which is M is defined to be a functor. If I fully normalize it, and if I'm able to use a keyboard, then the goal functor M turns into functor, and then they match up directly. Okay, good. Okay, so let's see if we can look at some examples. We could look at the standard Haskell examples, maybe, and IO, because that's defined in the standard library, and so on. But I thought we'd look at something slightly different first, and then we can get back to something like a Haskell example, but see that it makes sense in categories that are not sets. So I want to get back to Hutton's razor, which was this idea of having a really small toy language that just illustrates whatever we're trying to look at for the time being. So now I want to illustrate monads, so I've added in variables to my toy language. Right? So I have numbers like before, I have addition of numbers, I've taken out the booleans because they have nothing to do with what we're doing now. But I have added in variables. So I have some set of variables and saying that if you give me one of these, then you get that variable as an expression. So if you take this set to be empty, the empty type, then there are no variables and we're back to the old situation, right? If you take this set to be the natural numbers, then you have a first variable and a second variable and so on. So you have a countable number of variables. If you take it to be fin17, then you have exactly 17 variables. So we can be flexible about how many variables we allow. Okay. And the reason we do this is that if we want something to be a monad, then there needs to be a functor around, so there needs to be some kind of parameter to our construction. Right? And it makes a lot of sense to have index our expressions by a type of variables, because we don't have that here, but if we wanted to have something like binders, like lambdas, then when you go under the binder, you have one more variable in scope, right? So then you could change your set of variables from x to x plus 1, for example. So that's where it's coming from. But okay, so let's see if this type of expressions can be made into a monad. So the first thing we have to do then is we have to make it into a functor, right? And then we need to define a join for this functor and a return, and then that will hopefully get us a monad on set, because the type of this says that, well, if you give me a set x of variables, then I'm going to give you a set of expressions over those variables, right? So this goes from set to set. So we could hope that we have a monad on set because we have a functor from set to set. But let's see if we have the map first. So it says that, well, if we have a function from x to y, then we should be able to take expressions with variables in x and turn it into expressions with variables in y. Okay, so we could just see what we are asked to do. So we have the f, we have an expression e. Okay, I'm going to pattern match on the e because what else could I do? Okay, I'll do the standard renamings. Okay, so there's three cases. E could be a variable, a number, or an addition. If it's a variable, let's see what we have. So we have an x in x, and we want an expression in y, right? So of course, I could always return num17 if I wanted. That's an expression in y. But then I suspect that I will have trouble proving the functor laws then. So I'm not going to, f map of the identity is not going to be the identity if I give this definition, for example, right? So with that in mind, I think I should turn variables into variables and numbers into numbers and so on. So this should be var of something. Okay, and then we can see what we have. We need a y, we have an x, and we have a function from x to y. So it's a good case to actually apply the function. Right. Whereas if we have a number, then for the same reason, we want, if f is the identity, then we need whatever we give here to be the same as num of m. So we have no choice here really, right? This should be num of m. And similarly here, if f is the identity, we want to return an addition. And then here we better do some recursive calls. Right. Okay, auto is trying to screw us over. Right. Okay, let's see if we can prove that this is a functor. So let's see what we need to do. So we need to give an action on objects, an f map, and prove that it preserves identity and composition. So on objects, we want this to be expr. On morphisms, we want this to be the map expression we just defined. Okay, and then we have to see that if we now map, if we map with the identity, we should get the identity, which is an equation between functions. So we better use function extensionality. And then now we see that for every expression x, we have to show that if we map with identity on x, we get x back. Right. So I'm going to do this in a lemma. Okay, I'm going to do that again. I'm going to fully normalize before I ask for the type of lemma. Didn't work much better. Okay, I guess I need to do it by hand. So what we need is that for every e which is an expression, type x, so we have the x in scope. Let's see what we have. Going to ask for x to be in scope, okay. And then this is what I want. Okay, and rename this to E. Okay, let's see if the lemma fits. Yes, it does. Okay, pattern match on E. Okay, the variable case is the, in some sense, only interesting case, right? Because that's where we actually use the function. And we see that in this case, if the function is the identity, then this is what we expect it to be. So referral works. Num also just works. Here, we see that we have a plus on both sides. So COM2 of plus, and then 2 recursive calls should deal with it. Yep. Okay, so it's the thing we've seen before, where because map expression was defined by pattern matching on this thing, our proof has to pattern match on the same thing to just expose the structure, right? And it's going to be very similar here. We get x, y, and z in scope just in case. Okay, and then still want two functions to be equal, so I'm going to say x of something. And then here, just prove this by pattern matching on x, so I have to put it separate. Oh. Okay, I should have gotten the f and the g into scope as well. Lemma fit, yes. Okay, and it's the same thing again. This is stuck because we don't know what E is, so we better pattern match on E. The interesting case is the variable case, so let's look at that. And that's reassuringly simple. This case is also reassuringly simple. And here again, we see that we have an outermost plus on both sides. So it's going to be exactly the same as here. Okay. So it's just following the same structure to prove the thing we need. Okay, so we have a functor from set to set. Now we want this to be a monad. So let's see what we need. So we need a functor. That's our expr functor. We need a return, we need a join, and we need them to satisfy some laws, right? So the join, well, let's start with the return. So the return should be a natural transformation from the identity to expr. So let's see, that means that we need to have a transformation and we need to prove that it's natural, right? So we can kind of use Agda to remember what we need to do here. What does it mean to be a transformation? Well, it means that for every component x, we need to go from identity at x to expr at x, right? Because it was from identity to expr. So given an x, we need a function from x to x per x. Okay, what could this possibly be? Well, that's exactly the type of the var constructor, right? So we're saying that having variables is exactly that we have this return for the x per monad. It's saying that we can embed x into x per x. So I don't think we need to be doing more than that. Okay, what does it mean for this to be natural? So it says that if for every x, y, and f, right, so now the goal looks very simple, which is good. But what's happening is that on this side, we are first using f map of f, and then we are transforming, which was putting var, right? And on the other side, we are first putting var, and then we are doing an f map of f on the inside. Right? But it was defined to be exactly the same thing here, so we were lucky. So that's just true. Okay. If this, like we said before, if it's hard to prove naturality, then that's usually a sign that something has gone wrong somewhere. It's not, it shouldn't be hard. Okay, so we also need to join, which should be a natural transformation from x per composed with itself to x per. So again, we can ask, okay, what does this mean? Well, we need a transformation. So that says that for every x, we should be able to take an expression where our notion of variables are again expressions and squash it down into just an expression. Okay. So that's what this thing is doing here, right? And why have I prepared this as a separate function? It's because I'm anticipating that I probably need to pattern match to do this. I don't have a constructor that has this type immediately in my expression language. So we have to actually do some work to make this work. So I can put that in. Okay, and then after we defined it, we have to prove that it's natural, which says that if you map with a map, that's the same as mapping with whatever we define this to be. So again, this is the kind of thing where you look at what Agda tells you what you need to prove, and then you prove it. And it kind of makes sense at an abstract level, that it shouldn't matter if you transform and then f-map, or if you f-map and then transform. But concretely, you just prove whatever you're told to prove. Okay, but before we can do that, we have to define join expression, right? So let's see. So if we have EE, then we have to make just an expression. And again, we could just say num42, but then our naturality would not work, right? So we have to do this in a sensible way. So let's pattern match on EE. And okay, so I'm calling it EE because that's an expression with expressions for variables, whereas here we have actually exposed just an expression. Right? So it makes sense to just return that thing here. So we have reached the leaf of our tree, where we have, normally we have an x, but here we have an x per of x. So we're just going to plop that in, right? This is a whole expression in itself, and now we just remove the var constructor and we get an e, which makes some kind of sense. For numbers, again, we really have no choice, right? Just have to return the same number. And if we have a plus here, then again, we can just turn that into a plus and do recursive calls on the two sub-expressions. it's going to pick the wrong one again for me. Yes. So we are going through our term until we reach a variable, and then we just remove the constructor and put in the thing that was stored there, right? Which feels kind of natural, right? Okay, let's see if it is natural. Right, so now the goal has turned into something concrete because we know what join expression is. And we see that it's an equation between functions. So it's not going to just work with REFL, so we'll use function extensionality to prove it. Okay, so now for every x, which is an expression x per x, we have to prove something. So take this goal again. Here. Okay, does it fit? Yes. Okay, and it's again the same thing. This thing is stuck because we don't know what E is. So we'll put a match on E. Now these three cases. Okay, the var case, this is where things might and might not go wrong, right? So let's see what happens. Well, reassuringly, that's easy. Num case, what's happening here? Well, the map expression is just preserving the num, and the join is also just preserving the num. So all in all, both sides are just preserving the num, so that works. And kind of the same thing is happening here, right? Everything in sight is just preserving the plus, and I'm doing recursive calls. So if we do the same thing, then we see that recursive calls work perfectly fine here. It's all doing the same kind of recursion, so it's working out. Okay, so we have these two natural transformations. Now we need to show the laws that if we needlessly inject a var and then remove it again, that should not do anything. Well, that was the easy one, where it's just true, right? Because we are putting a var on the outside and then removing it immediately. That's okay. Here, we are mapping, putting a var on the inside, and then we are removing it. So now it's not immediately true that this is the identity, right? But we could still hope the pattern match on the x if we use ext. And show that it's true, right? So let's see if we can do that. So I'm calling all of these things lemma because then I don't have to think about what to call them. Okay, x is not in scope. Okay, that's the lemma fit. Yes. Okay, why is it stuck? Well, it's stuck because we don't know what E is, so let's pattern match on E. Okay, it could either be a var or a num or a plus. Okay, let's look at the var case. That's the interesting one. And we'll see what's happened here. So E was a variable, so we were mapping var across the variable, which means that we are putting a var on the outside. So this thing is going to be a var of x, and then the join is going to remove that same var again. Right? So it's going to turn it into a var of x, whereas on the outside we just have a var of x. So that happens to work. And in the num case, it's usually simple. In the plus case, everything in scope is just going down structurally to on E and E prime. So press standard Kong2 doubled such more. That just works. Okay, and the final thing we had to show was that it doesn't matter in which order you join three things, right? Could either start by joining them on the outside and then joining again, or you could start by mapping, so joining on the inside and then joining again, and that should be the same, right? And again, this is not obviously true, so we have to look at the x using to bring the big X into scope and use function exponentiality. And this is the thing I need to prove. Okay, this is EE. Does the lemma fit? Yes, it does. Okay, so pattern match on EE. Rename things. Okay, bar case is the interesting one. And we see reassuringly that things work out. Num case we expect BC, and it is. And in this case, again, everything is here structural, right? So we have a plus on both sides. So we just do two recursive calls. It will work out. Right. Okay, so we managed to define a monad on set. And what does the bind for this thing do? Right, because for every monad we define the bind operation, right, using the join and the fmap. So we can now do it for this particular monad, and I can ask for the type of this bind operation, fully normalizing it. Right, that wasn't too bad. Right, it's saying that if I have a function from A to expressions in B, and I have an expression in A, then I get an expression in B. If I rename this a little bit, call this X, because I'm thinking of this as variables. Then if you squint enough, saying that, well, if I have some way of turning all the variables into B's, and I have an expression with possibly some variables in X, then I get a B. So this is the type, at least, and you can check that it really is, but it's the type of substitution. Right? Saying that for every variable I get something, then I can lift that to whole expressions and substitute all the variables for the thing I want. So another way to see the fact that express a monad is that we have a substitution operation for expressions, right, where you can plug in new values for your variables. And we derive that by instead saying that, well, we can squish expressions of expressions into just expressions. And we can fmap over here. So here you can kind of see where the substitution is coming, right? Because the fmap is really applying the function to the variable. And then the join is possibly removing the variable, so leaving the thing that you wanted to substitute for the variable there. So that's another way to possibly think of monads, is to saying, well, you have some kind of expression language and you have a way to substitute, then you have a monad, right? Which is sometimes helpful rather than always thinking about effectful operations. Okay, I think we should stop here and we'll look at another example tomorrow. which is not an example on set, but on a different category, just to see that it makes sense there as well. And then next week we'll also see where the laws are coming from, why they are useful. But we'll save that for then. Are there any questions?
Yeah, what did you command you use to work backwards there?
Sorry?
What command did you use to work backwards there to get the
Get the type.
the definition?
Right. So what I did was, we can do it again quickly. So I said, okay, I want to define bind for expert. I don't know what the type is. I'll put a question mark. That's what I do when I don't know what's going on, right? Then I say, well, I don't know what the definition is. I'll put a question mark for now. I load. Actually, I do know what the definition is. So I'm just going to say bind of expert monad. I'll quickly check that what I have here makes kind of sense, and then I give that. It's definitely going to type check because this is something unconstrained, right? I reload, and then at this point, there's only one thing that can really fill this goal, right? Which is whatever the type of this is. So I say, okay, fully normalize, Control U, and then solve this goal for me, please. Control C, Control S. And that's filling in the only solution that makes sense. So that's a good trick to know that if you're too lazy to give a type, but you know what the term is, you can fill in the term and then solve the type instead. Right? So it doesn't work if your term is, say, 7, because that could be overloaded. Right? But if you have something which is not overloaded, then it works. That's a good question. Okay, should we stop here?